Section 9.5 in your book is on how to do calculus with polar equations. The important equations, the new ones, are how to find the area under a polar curve. So a polar curve can look like lots of different things. Could be a circle. A lot of them kind of look like these heart-looking things where it comes up and then maybe like bends in. So if we need the area of this, you would start with whatever angle gives you that point and integrate to whatever angle gets us back to that point. So A and B are both angles here. They're both radian measures. It's 1/2 the integral from A to B of r squared d theta. And then arc length would be the distance. So starting here and coming all the way around and getting back to here. Is this formula here, square root of, it's basically r squared plus the derivative of r squared d theta. Other formulas, ones we've already looked at, we know that the y value is equal to the radius times sine theta, and the x value is r cosine theta. We did that way back in Unit 1 when we reviewed some of pre-cal stuff. So example 1 says to let r equal 2 minus sine 2 theta, and we are asked to find the interior area and the perimeter. So we can use the formula here. We have 1/2 the integral of r squared. So 2 minus sine 2 theta squared d theta. We need to figure out what these bounds are, though. We don't know what bounds makes it go all the way around. Sometimes it might be 0 to 2 pi. Sometimes it might be something else. So let's sketch a rough graph here of what this is going to look like. If I plug in 0 for theta, so 0 for theta, I have 2 minus sine 0. Sine of 0 is 0. So the radius is 2 and the angle is 0. If I plug in pi over 4, plugging in pi over 4 gives me 2 minus sine of pi over 2. So at pi over 4, now my radius is down to 1. If I plug in pi over 2, 2 minus sine of pi, it's back at 2. If we plug in, let's see, we did pi over 2. Next one would be 3 pi over 4. So we'd have 2 minus sine of 3 pi over 2. So at 3 pi over 4, it's out here at 3. At pi, we'd have 2 minus sine of 2 pi. So we're back at 2 again. 5 pi over 4. 5 pi over 2. So 5 pi over 2 is all the way around, and then 1 more pi over 2. So sine of 5 pi over 2 is 1. So 2 minus 1, we're back at 1. And so on. 3 pi over 2 times 2 is 3 pi. That gives us 2. This one here, 7 pi over 4. So 7 pi over 2. 7 pi over 2 is down here, -1. So that one's 3. And 2 pi sine of 4 pi, 2 minus that gets us right back to where we started. So this is an awful graph. I'm sure it doesn't look quite like this. But 0 gets us here, and we go around, and once we get back to 2 pi, that does put us back where we started. So our bounds here should be 0 to 2 pi. It's possible that 0 to pi is going to get you right back to where you started. Next it asks for the perimeter. Equation for perimeter is the integral from a to b, integral from 0 to 2 pi of the square root of r squared plus the derivative squared. So dr d theta, the derivative of this is negative cosine 2 theta times the derivative of 2 theta. So that'd be the setup on both those. Let's go ahead and evaluate that real quick with the calculator. These, again, are usually calculator problems. Not necessarily always, but... so in part A, we've got 2 minus sine 2 theta squared. And we are integrating from 0 to 2 pi. Times 1/2. Gives us 14.137. And then to find the perimeter, I would probably go down to y2. We already have that squared under y1. So it's going to be the square root of y1. It's already squared plus negative 2 cosine 2 theta. Close the parenthesis around the 2 theta. Close the parenthesis around the negative 2. Now it's squared. And turn your first graph off so that when you integrate, it's only integrating the second graph. So the distance around here is 15.404. Part C asks us to find the value of dy d theta at theta equals 2 pi over 3. Remember, our y value is equal to r sine theta. So y is equal to r, 2 minus sine 2 theta, times sine theta. And we are asked for dy d theta. So dy d theta would be the derivative of this, which is negative 2 cosine 2 theta, times that, we're using the product rule here, plus this times the derivative of that. And then plug in 2 pi over 3. Again, since it's a calculator problem, you could do it with the calculator. It would probably be easier than trying to do it by hand, although it could be done that way as well. I'm going to store 2 pi over 3 as x and type in our equation. Negative 0.567. Another way you could do this, if it is calculator, let's get rid of the squared here. So that's r. I want the derivative of r sine theta. So I want the derivative. So y2 is y1 times sine x. Just graph the y2 graph, and then we're going to calculate the derivative at 2 pi over 3. And we get the same answer. And part D, that's a long problem. Part D asks for dr dt, given that d theta dt is 2. So we know r is, what was it, 2 minus sine 2 theta. So we want dr dt. So the derivative of this is going to be negative cosine 2 theta. And then times the derivative of the inside, so times 2. And then because we're taking the derivative with respect to time, we also need to multiply by d theta dt. Theta is 2 pi over 3, so I've got 4 pi over 3. And d theta dt is 2. 4 pi over 3, 1, 2, 3, 4 pi over 3 has a cosine of negative 1/2. Negative 1/2 times negative 2 is 1 times 2. Example 2 asks us for all points of intersection for these two polar graphs. 1 minus cosine theta and r equals 2 plus cosine theta. So here what we want is we want the intersection points of these two. So for the same theta value, we want the radiuses to be the same. So substitute over here, 1 minus cosine theta is equal to 2 plus cosine theta. And we're solving for theta. Add cosine theta to both sides. Subtract 2. Divide by 2. So we want to know when is cosine negative 1/2. Cosine's the x value. If we count by pi over 3s, we've got 1, 2 pi over 3, 3 pi over 3, 4 pi over 3. And when theta is 2 pi over 3, I would have 1 minus cosine of 2 pi over 3, which is negative 1/2. And same thing here. These are our two intersection points. If it wanted like the actual xy coordinates, you would use x equals r cosine theta and y equals r sine theta to find the rectangular coordinates of those points if you needed them. Example 3 wants us to find the area of this little shaded region right down here. The area of the inner loop, and they give us the equation, 2 plus 4 cosine theta. So again, we know the formula, 1/2 the integral of r squared. The problem is we don't know what these angles are that make the inside region here. So again, I kind of start plugging stuff in. So if we plug in 0, we get 2 plus 4. Cosine of 0 is 0. So theta is 0, radius is 6. That's that point right there. This one looks like it's at pi over 2. I would confirm that. If I plug in pi over 2, I get 2 plus cosine of pi over 2 is 0. So that is pi over 2. Notice anytime we reach this point right here, that's when the radius is 0. So we started here, we're coming this way. That's at pi over 2. To find this angle, I want to know what radius makes that, or what angle makes that radius 0. And then it comes this way, and we hit it a second time. We want to know which angle makes the radius 0. So that point, both those points have a radius of 0. So let's set the radius equal to 0 and solve. And we get cosine is -1/2 again, which we just found was 2 pi over 3. So that's this point right here the first time I pass through it. And then when I go around and reach it a second time, that's the 4 pi over 3. So our equation is 2 plus 4 cosine theta. And I want to integrate that equation squared. The integral from 2 pi over 3 to 4 pi over 3. And then don't forget to multiply by 1/2. And we get 2.174. Last one, example 4. Asks a couple different parts here. Part A wants the area of the shaded region. Area of the shaded region. So notice what we're doing is we have the outside circle, and then we need to take out the area of the inside circle. I guess they're not circles. This one is. But we have this blue figure, and then we have this red one. If I take the area of the blue one and subtract out the area of the red one, as long as I only go from this value here, starting at this angle and ending on this angle, because notice for this part over here, we're not taking the blue area minus the red area. So we want to start with this angle, go all the way around to this angle right here of the blue area minus the red area. So first thing we need to do is find what these angles are. To find these points of intersection, we set the equations equal to each other. This time we get sine is -1/2. Sine is -1/2 at these two values. What we don't want to do, we do not want to say theta equals 7 pi over 6 and 11 pi over 6, and then integrate from 7 pi over 6 to 11 pi over 6. And the reason for that is if I go 7 pi over 6 is my starting one, and then I go to 11 pi over 6, it's going to take this blue area here and subtract out the red area here. What I want to do is I want to start at this value. We also can't start at 11 pi over 6 and go to 7 pi over 6 because it's going to start here and just go this way, which is not what we want either. So instead of calling that 11 pi over 6, what we want to do is we want to call that negative pi over 6. Here's my angle of 0, and then going back pi over 6. So negative pi over 6 starts at this one, and then it's going around to 7 pi over 6. Of the outside circle, 3 plus 2 sine theta squared. So that's going to give me all this, starting at this angle, ending at this angle. It's going to give me all this area. And then I want to take out the part that's inside the circle here. I'm going to take that out. So take out the area of the circle. The radius of the circle is 2. And again, we can do this on our calculator. I'm going to set it up as y1 is equal to that 3 plus 2 sine theta. Y2 is equal to 2. So we want y1 squared minus y2 squared. Starting at negative pi over 6 and ending at 7 pi over 6. Times 1/2. Part B wants the interior area, so the area that's inside both. So we are looking for this area right here. So inside this one, but then also inside this guy here. So again, we're going to break this down. So here's our intersection point, here's our intersection point. And what we're going to do is starting here and going this way until we get to here, we want to integrate the circle. So that was starting at negative pi over 6 and going to 7 pi over 6 of the circle. And then we need to add to that, starting at 7 pi over 6 and going to here, which is 11 pi over 6. And for that, we are integrating the, whatever that thing's called, a little heart-shaped thing. So we need to split it into 2 separate integrals. So first, let's do y1 squared. Y1 is this one, so that's the one we want to go 7 pi over 6 to 11 pi over 6. So 1.993. And then integrate y2 squared. starting at negative pi over 6 and going to 7 pi over 6. So that's 8.378. Plus the one, I got 2 plus signs, plus the 1.993 gives us 10.370. So that's it for the notes.